let's practice. Let's calculate the relative atomic mass of chlorine using the percent abundance data provided. We have two isotopes of chlorine, chlorine 35, chlorine 37, and we have their percent abundance. So take a moment and calculate the percent abundance, or sorry, calculate the relative atomic mass of chlorine. So you should have written an equation, something like this, 75% times 35 for chlorine 35, and then 25 times 37 for chlorine 37, divided by 100. You should get 35.5. All right, this is the weighted average, the relative atomic mass. And if we think about what this means, right, in a sample, this is the average mass of the chlorine. Even though no single chlorine atom has this mass, this relative mass, it is the average mass of all of them, right? So let's do a couple more questions. Rubidium has two common isotopes, rubidium-85 and rubidium-87. If the abundance of rubidium-85 is 72.2% and the abundance of rubidium-87 is 27.8, what is the relative atomic mass of rubidium? So let's take a second. Let's do this one first, then we'll do the second question. See if you can figure that out. Okay, so throw this up on there, right? You should have followed the same procedure, right? 72.2 is our percentage. That's times rubidium-85 plus 27.8. That's our percentage of rubidium-87. Multiplied by 100 gives you 85.556, right? All right, let's do number 2. This one's not as straightforward. You have to use a bit of math to solve this one, a bit of algebra. So silicon has 3 stable isotopes, silicon 28, silicon 29, and silicon 30, right? The heaviest isotope has a percent abundance of 3.1%. So the heaviest isotope has this percent abundance, right? Using the relative atomic mass from the periodic table. So you're going to have to look at your periodic table. Calculate the percent abundance of the lightest isotope to 1 decimal place. So you might have to really think this one through on what it means and how to do it, but take a minute or two and try to complete this question, and then I'll kind of run you through it. Okay, so this question, I'm gonna throw this up on there, and I got this on offline because it's easier than creating the whole calculation on the computer. But the answer is 94.1%, so if you got that, good job. This is kind of a hard question. The way that we want to think about this, or the way that I think about this, is multiplying our um, our isotope masses by our percentages, but we're not going to do percentage, we're actually going to do the decimals. So divide the percentage by 100, right? So instead of 3.1%, it's 0.031. So we have this, our isotope, our heaviest isotope, silicon 30 times its abundance plus this will be the abundance of silicon 29, and this will be the abundance of silicon 28. And it's going to equal what you found on the periodic table. So this is the average, which we know, and we know that silicon 30 has a percent abundance of 3.1%, which in decimal form is 0.031. We are looking for the percent abundance of the lightest isotope, so we're going to call that X, right? And then the abundance of this other isotope will be the leftover abundance, which is 96.9 from this, right? That's just 100 minus this. but in decimal form, minus whatever our abundance is from this 28, um, silicon 28. So you can do a bit of algebra and solve for x, right? If you're not super comfortable with this algebra, please let me know. Send me an email or something and we can go over this. But basically we're just simplifying, right? Multiplying these together, multiply 29 by each of these, you get 28.101 minus 29x, and then plus 28x. You're doing some more simplifying. Eventually you get to x equals 94.1. And this is the percent abundance of our lightest isotope. Um, so this one is a little trickier. You're going to need to do a little bit more math. But these problems, it's just a little bit of algebra that you need to think through a little bit. Okay, so here is a question for you. Why might we substitute one or more atoms with a distinct isotope during a chemical synthesis? So when we're synthesizing, that means making a new thing, right? Why might we substitute an isotope? Like, for instance, most carbons are carbon 12, but in this case, they're putting a carbon 13 in this synthesis. I know this is a lot to look at. You don't need to understand what it all means, but why might we put a carbon 13 at a specific point, for instance? This is a big chemical structure at this point. Think about that for a second. So, there are lots of reasons. In this case, right, that carbon 13 is like a marker. It's as if you went onto the molecule and you marked that carbon with a Sharpie. So when you are synthesizing, which is a tricky business, right? Lots of things can happen during a synthesis. Um, when we put that carbon 13 there and we get an end product and we get like down here, right? There's 77% of our sample, there's a carbon 13 here. That is telling us that this carbon is changing in a certain way, which gives us more information, right, to then do reactions in the future. So it allows us to identify possible reaction mechanisms, which are like, how is this actually working, right? Why is this working? Sometimes we throw chemicals together and we get new chemicals, but chemists want to understand each of the steps, right? So these markers help us understand the steps because we now have a marked carbon. We've marked it with a Sharpie or an isotope. So when we see it in the end product, we can figure out, or it helps us figure out some of the steps, right? Okay, so here's one last question for you. Rubidium contains two stable isotopes, rubidium-85 and rubidium-87. Using the relative atomic mass from the periodic table, so you have to look that up on your book, calculate the percentage abundance of each isotope in pure rubidium. State your answer to three significant figures. I think that you've heard about significant figures before. If not, we will definitely talk about this some more when I get there. But basically, just give me 3 digits in your answer. Yeah. So try this out. See if you can figure it out. And then I will talk about the answer. Okay. So again, I got this answer offline. It's just easier than having to do it all on the computer. But it's similar to that one with silicone, right? A little bit different, but kind of similar. We know that the average that we get from the table, the periodic table, is 85.47, right? And we are looking for the percent abundance of each isotope in pure rubidium. So here is our isotope weights, 85 and 87. And we can say that the abundance of one of them is x, and the abundance of the other is 1 minus x. Because remember, when we do percentages in decimal form, 1 is 100%, and then anything less than 1 is like the percentage. So, for instance, if we solve for x, that will give us the percentage of uh, rubidium 85, and then we can subtract that number from 1, and that will give us the percentage of rubidium 87. So if you do a little bit of algebra, right, we multiply 87 by 1 and by x, we get this right here, and then we simplify it to this, right, and eventually we get x equals 0.765, which we multiply this by 100 now to get a percentage. This is decimal form. Percentage, you multiply by 100. And we get 76.5%. You can then do 100 minus this to give you 23.5%. So 76.5% rubidium 85, 23.5% rubidium 87. So as you get these more difficult questions, remember that you can put an x and 1 minus x or abundances minus x to represent what you're looking for. Because you usually have enough information to create some sort of equation like this. Okay, that's all I got for you today. We don't really have time to get into the mass spectrometer stuff, so I'll go over that in our next lesson. Um, and I hope you have a great rest of your day.